of sodium methoxide of its conjugate acid. 16. So, since this is less basic, since this isn't a strong enough base to deprotonate this fully, we have to do what? Use excess. Use Le Chatelier's to our advantage. And so normally we use like 5 or 10 equivalents of sodium methoxide to drive the equilibrium to the enolate. So excess sodium methoxide, and so what we usually do this is ethanol, and we usually do this warmed up or room temperature. So I'm just going to go parentheses warm. So this reaction is very reversible, right? So if the deprotonation is very reversible, is it going to give us the kinetic or the thermodynamic product? That's going to give us the thermodynamic. And in this case, the thermodynamic. So let's be honest, it's going to deprotonate this one first. But if we deprotonate this and run ethanol, we can just reprotonate with ethanol to give us the starting material. So it's very reversible. Eventually, what we will get out, that was a really will be the more substituted enolate. So why is this more thermodynamically stable than the less substituted? This is a concept we've talked about a few times in this class. Zytas rules. More substituted olefins are more thermodynamically stable. So since this enolate is a more substituted enolate, a more substituted olefin, it's more thermodynamically stable. So the more substituted enolate is going to be our thermodynamic enolate. So in general, if you see LDA being used as a base, that means it's going to give us the kinetic, less substituted enolate. If you see sodium methoxide being used as a base, that means it's going to give you the thermodynamic, more substituted enolate. Okay? Makes sense? Kinetic versus thermodynamics all there. So this will be 2, which is going to be higher energy. We'll call this 3. So this is more thermodynamically stable. So if the protonation can go back and forth when you use a weaker base, like sodium methoxide, and that's the reason it can go back and forth, because we're using a weaker base, then when it deprotonates and it gives ethanol, which is a decently strong acid, which is actually more acidic than the alpha hydrogen is, so that will obviously be protonated. And we have to use excess sodium methoxide to drive the reaction towards the enolate using Le Chatelier's. And so it's highly reversible and gives us a thermodynamic. And so then, of course, what we can do with each of these enolates, we can take an alkyl iodide. So in this case, let's take ethyl iodide. So under kinetic conditions, the product of an alkylation of the enolate would be something that looks like this, where the less substituted carbon got the electrophile. In this case, ethyl iodide. Or if you used X2, the less substituted olefin would get the X. Whereas under these sodium methoxide ethanol conditions, if we throw in ethyl iodide, the product we will get out will be the more substituted carbon getting the alkyl group. So I'm going to do some examples. Here. So in general, under kinetic conditions, the less substituted carbon gets the electrophile. Under thermodynamic conditions, i.e. sodium methoxide, the more substituted gets the carbon. All right. So with this substrate, if I get on a test, I were to give you this plus sodium methoxide, ethanol, and Br2, what would the product be? Thermodynamic. So we'd replace one of the CH groups, the more substituted CH group, alpha hydrogen. So we'd replace this carbon's hydrogen with the bromine, right? We get a product like this out. So the more substituted carbon gets the electrophile under thermodynamic conditions. So here's another base we like to use besides lithium diisopropylamide. We call this sodamide, sodium amine. So it's called sodamide for some reason. So will this be a kinetic or thermodynamic base? Absolutely, it's still really strong. It's not sterically hindered, but it's still really strong, so it's still going to favor the first thing to be protonates, which is going to be the less substituted. So it will still give us the kinetic base, because it's a really, really, really strong base. And then some domain electrophile you think would be good for this, any electrophile. All right. To give us something that will look like this. So kinetics versus thermodynamics is kind of an important thing. Question: what would happen if you used butyl lithium as our base? Would using butyl lithium be a good or bad idea as our base? Yes. Why is butyl lithium a bad idea for a base? It'll add in. And whereas this could add in too, it's an amine, so it could leave and give us an amine back. Whereas butyl lithium will irreversibly add into the carbonyl. So we'll get a menagerie of products. So you want to use a base that's not going to add into your carbonyl, so you want to be careful. Synthetically speaking, what do you think alpha halogenated ketones would be useful for? What kind of chemistry? If you make the molecule, what do you think you would do with it next? Synthetically, what transformations can you do with an alpha halogenated ketone? Or aldehyde or ester or whatever. Exactly, SN2 chemistry. Or any chemistry we've talked about that we do with halogens. You could do phenylcrafts, alkylations, for instance. The one thing to worry about dealing with things like this is we have two electrophiles, right? We have a ketone and we have an alpha halo ketone. So what we want to make sure is we don't want to use nucleophiles like butyl lithium or Grignards because they will just add into both. For instance, if you take this molecule and threw an LAH, it would do an SN2 because LAH says SN2s, but it would also reduce the alcohol, the ketone to an alcohol. So if you used a strong nucleophile like LAH, we would not have our ketone anymore. It would just look like this. So what we want to do instead is use nucleophiles that will only add reversibly the carbonyls. Just give me an example of some nucleophiles that will add reversibly the carbonyls. Think acetyl chemistry. We've been talking about nucleophiles that add reversibly the carbonyls the last couple of weeks. So anything like HO minus or NH3, any of these nucleophiles that we've talked about with acetal and amine and iminium formation are good nucleophiles for this chemistry. So whereas LAH will just add into anything it can, if you just use sodium hydroxide, the product we would get out would be the SN2 just reacting with the chlorine. And that's because if sodium hydroxide were added to carbonyl, it would just revert back to the carbonyl again. So nucleophiles that can reversibly add to carbonyls are good for doing further chemistry with these alpha substituted haloketones. So let's just look at some of this. So let's just keep doing examples for the rest of the class, which will kind of lead into what we'll talk about on Monday. And as I'm erasing this, my goal for the exam is to get through the aldol reaction, which is in chapter 18. I will definitely get through the Claisen reaction, which is the beginning of chapter 18, but my goal is to get to the aldol. If I don't get to the aldol, the test will just be through the Claisen, but just for you guys studying ahead, my goal is to get to the aldol reaction. Alright, so again, kinetic, thermodynamic, or it doesn't matter. Which one of these protons, which enolate will we form? So which alpha carbon will be deprotonated for this substrate? Kinetic, thermodynamic, or doesn't matter? It doesn't matter. Because in this case, this is a different case, right? Because now one of our substituents on the ketone is an electron group. And on Wednesday I talked about the acidity of dicarbonyls. And what I mentioned was for dicarbonyls, so an alpha carbon with 2 carbonyls on each side, because now we have doubled the resonance, they're significantly more acidic than a typical ketone. So whereas a typical ketone, so this carbon-hydrogen bond will have a typical pKa of 20. But this hydrogen has a pKa of 10. And that's because the resulting minus charge can resonate into this carbonyl, and it can resonate into this carbonyl. So we have twice as much resonance I'm so used to equilibrium arrows, I apologize. That should be a resonance arrow. There's twice as much resonance, which means twice as much delocalization. Which means twice as much stabilization, which means a lower pKa. So in a case like this, because these protons are 10 orders of magnitude more acidic than a typical proton, we don't have to worry about kinetics thermodynamics. Because there's a 10 order of magnitude to go here, just because it's more resonance. And so what that means for a chemistry like that, if we wanted to do any alkylation of this, we don't need to worry about using LDA. We don't need to worry. We can use any base because these are so much more acidic. So an example of one of these diketones is you can stick with sodium methoxide. And then you can use your electrophile. Let's just use methyl iodide because it's easy to draw. And then you form this enolate here. And that's going to attack the methyl iodide so the product can get out. Would be the alkylated carbonyl composition. So when you have a marked difference in acidity at a carbon between two different carbons, then we don't have to worry about kinetics and thermodynamics. It's just the more acidic proton gets deprotonated. And then the last thing I want to mention, as I said, the deprotonation I showed you with non-symmetrical ketones is the most hard example of anything. So any other deprotonation is going to be cake. So just to give you a quick example here, if you just have a monoester and you want to form the enolate, you don't have to worry about kinetic thermodynamics. So you just need to find a strong enough base that will deprotonate this. And so you can just use LDA and not worry about kinetics and thermodynamics to get your enolate from your ester. So I showed you the most difficult deprotonation to form an enolate with ketones. Everything else is the same but easier.